So everybody asks, what is a quantum computer? Let me try to elaborate a little bit more on that. What is a quantum computer? A quantum computer, compared to classical computer, is a computer which is working with so-called qubits, not with classical bits. With classical bits, you have a 1, you have a 0, and you calculate things are known since years. A quantum computer that's based on principles of quantum physics, invented almost 50, 60, 70, 80 years ago, is calculating with qubits, but not in a state like 1 and 0. It's using physical problems or physical things like superposition and entanglement to calculate things differently. Quantum computer can very good work on optimization problems. You can run algorithms for optimization of chemistry, chemical processes, for example. Quantum computers are already today used to find ways through cities, incorporating the traffic jams inside of a city. But as well on a quantum computer, and this is something you cannot so easily do, you can do cryptanalysis. What is cryptanalysis? Basically, cryptanalysis is you try to figure out the secrets of an algorithm, of a cryptographic algorithm like an RSA, elliptic curve, and out of the public information of the public key, you try to retrieve by mathematical operations the secret key. A classical computer cannot do that very easily. It takes a lot of times, but a quantum computer, once it's powerful enough, so-called universal quantum computer, might affect and will affect classical cryptography like RSA and elliptic curves. So in short, a quantum computer, which is in place already from some big guys like Microsoft, Google, IBM. They're all working on quantum computers, and you already can rent space and computing time on quantum computers. A quantum computer can do a lot of good things, like I said, the optimization of processes. But on the other hand, it can be used for things like cryptanalysis, which could be used in the end ultimately by hackers to attack cryptography in all kind of forms. All kind of forms, what does that mean? Well, that would not only affect, for example, the cryptographic communication in the internet, but it would affect as well all kind of ID documents, because all electronic ID documents rely on cryptographic schemes and logical algorithms, and with a quantum computer it's quite easy to attack those kind of algorithms. So the quantum computer, what can you do against this kind of cryptanalysis? Well, basically in 2017 there was a big competition started by the American Institute for Standardization, the NIST, finding new ways of cryptography which are safe and resistant against a quantum computer. So, which will ultimately replace classic cryptography like RSA and elliptic curves. These so-called post-quantum algorithms are algorithms which are supposed to run on a standard ID card, on a standard passport, on a standard, healthcare card. And these algorithms are supposed to be safe against both quantum computer attacks, but they should of course be safe against classical attacks, classical fault attacks, classical side channel attacks. This post-quantum cryptography, this process takes quite a while to find the right algorithms because they need to be performant. Basically, they need to be safe against quantum computers and the rest. And after roughly 5 years of competition and analysis, now in 2022, the first candidates have been selected as the most promising candidates, replacing the OLED cryptography. There were algorithms amongst those like XMSS, like Kyber, like the lithium. And The NIST and the institutions working with that organization as well. There is industry, there are all kind of security institutions. There's the target to finalize all of the algorithms until end of next year, end of 2024. And to having a set of cryptographic algorithms safe against quantum computers. One important thing is, because that's always confused, post-quantum and quantum cryptography, that's different. Quantum cryptography, that means you use a quantum computer to run cryptography, which is good. Yeah, you can secure communication over the ocean or in the internet or whatever, but that's not really suited because a quantum computer currently takes a size of a building, actually a quite large building. You cannot put that into a passport. Post-quantum cryptography is not supposed to run on a quantum computer, but it's supposed to be safe against attacks by a quantum computer. It's supposed to run on a standard security controller fitting into a small ID card into a passport. So that's post-quantum cryptography. What's Infineon's role inside of that? Infineon was not only actively contributing into the competition, we are continued since more than 5 years working on these algorithms, because finally, even if the algorithms are chosen, there's a lot of work to do in terms of standardization, in terms of implementation efforts to be integrated into products, that ultimately, that in the end, the products are safe again. In concrete as well, for that, Infineon is heavily investigating, especially in security attacks on the algorithms. We're working on all kind of standard attacks like side channel attacks, fault attacks, especially fault attacks on the new algorithms to speed up the process to have them available in time. What does availability in time mean of those post-quantum algorithms? Well, basically, as of today, the quantum computer, which exists today as well, is not powerful enough to really crack an elliptic curve, to really crack an RSA. But if you ask the industry as of today, when will the quantum computer be powerful enough, you get the answers, might be next year, might be in 5 years, might be in 10 years. But still, for an ID document, even if the quantum computer is powerful enough in 8 years, then with the documents you bring out to the field today, which are valid for 10 years, then you still have a problem, because it's not so easy to withdraw documents out of the field, which are in the thing for 10 years. So even if the quantum computer is there in 8 years, you need to incorporate, as of today already, countermeasures to be quantum safe. That's the reason why Infineon is heavily invested into those topics, and we didn't start this year. We already started, I think it was prior 2015, working on the topics, because these topics really take time. Standardization of algorithms take time. Secure implementation take time. And what will take time as well is the standardization in overall infrastructure, like the ICAO infrastructure worldwide, like how to define a specific infrastructure in the country for a healthcare card, where you have local specialities, so to speak, and in the end, to really start project trials and to really start ramp up of those kind of products, quantum safe products which are safe against a quantum computer. We expect the transition times will take quite some years. And that's mainly the reason why Infineon is always giving the consultancy to governments to start investigating now, to start preparation right now for a transition phase, how to integrate that into local projects, how to integrate that into the infrastructure, because basically, once the quantum computer is really powerful enough and there, then it's already too late, because then the government still has documents for 10 years in the field, and then basically it's too late. That's the reason why Infineon has already started since years.